Hi, everyone. So I think we have given sufficient time to everyone to log in. Let's start now. My name is Anna Paleolog. I am the project coordinator of AEGLE, and I will give you a small brief presentation of the project so that you have the general overview of how it all started. So today we are going to present the clinical decision support system. This is the fourth webinar in the series of webinars we have launched, and this is the last one of the prototype. So the project aim has been to improve the performance of healthcare, which is a simple statement but not so easy to achieve. How do we do this? We have tried to get insights from medical data after processing this data. And the challenge, of course, was that the enormous amounts of data is not so easy to process. So there is a lot of infrastructure needed in the background. There is a big need for intelligence, for efficient analytical engines. And at the same time, while improving the performance, we are also striving for achieving a reasonable price to reduce the healthcare costs. To come up with the best pricing for our platform, we have launched a questionnaire which is running currently, which you can access at the link provided in this slide. You can also find the link on the website of AEGLE to fill in your opinion about this. The project solution of AEGLE offers a platform for big data with libraries of standalone analytics. So it is not only providing the infrastructure in the background, but also the specific analytics for each use case which we are examining. For whom is the platform? The platform is targeting users from the research community, both from the industry and the universities and academia. So the researchers mainly use the platform to generate different hypotheses and test them and come up with new solutions for existing healthcare problems. At the same time, the platform is useful for the healthcare planners who are using it or can use it to improve the public health from aggregated analysis of the results. Finally, what we are going to present today is mostly targeted to clinical practitioners who are taking decisions every day to support the patients in the hospitals and other healthcare institutions. We have worked with 3 featured use cases in this project. These were the intensive care unit, the non-malignant chronic diseases. In particular, we have worked with diabetes mellitus type 2, and finally, the chronic hematologic malignancies, and in particular, chronic lymphocytic leukemia. We have already presented the research and development platform for researchers, and today we are going to present the user interface for the clinicians. So this is the last webinar of the series. I would like to urge you to demonstrate your work in a conference that we are organizing. So we would like to share the final release of our platform in this conference in Rotterdam during May 17th, 18th. But we are also inviting everyone else who has worked on big data solutions, either in a European project or in a startup initiative, to come and present their work in the conference. This would be all from me for now, and I would like to give the floor to Katerina Vaporidi, who is going to present the use case of the ICU in brief.
Thank you, Anna. Thank you all for being here. Okay. So I will try to briefly describe the specific clinical problems of intensive care that we have tried to address within this project. The result is a user interface for clinical decision support that you will going to see right afterwards. Now, the main problems we have focused is the personalization of patient care and early detection of deterioration, and mechanical ventilation, specifically focusing on patient ventilator interactions. One particular need for clinicians is to be able to review multiple biosignals from different sources to understand the patient's condition. Although we may think that physicians are indeed 24/7 present in the intensive care, not everybody is there at the same time. And when we all as a group need to understand what's happened to the patient to take appropriate actions as next steps, we need to be able to review what exactly has happened. That means that we need to see different parameters from different sources. This is not feasible currently in intensive care. So we have tackled some specific problems, and I will briefly introduce them. One of the major problems in intensive care is providing the optimal nutrition. Although we consider that providing the best nutrition would improve patient outcome, this optimal nutrition level is not easily provided or even defined. At the bedside, it is difficult to compute the needs of the patient. The formulas are quite complicated to be done on the bedside. Even if we spend half an hour computing the needs of the patient, it is not known or set in the literature what optimal target should be set. So specific groups of patients should have other optimal targets. And based on the current literature, physicians can choose any given target between 50 or 100% based on their personal judgment of the currently available data. Someone may believe the study that said 50% is just enough and does not offer. Someone may not believe that study and think that he should target for 100% or perhaps a different target. So we think that it should be at the hands of the physician to set the target for nutrition. The CDS solution offers the calculation of the needs of the patient based on the most accurate currently available formulas and the most complicated ones too. It has input on the ingredients of the formulas available for nutrition in intensive care. So based on the formula that the patient is receiving, the CDS provides information on the deficit, if any, the patient has. This allows for visualization of delivery and, of course, appropriate alarms when a physician set target has not been achieved. Moreover, in AEGLE, we have developed predictive analytics based on nutrition and other electronic health record data, which indicate patients at high risk for death based on their clinical and nutrition parameters. These alerts are also available on the CDS solution. Another clinical problem is the analysis of electronic health record data. What are the problems here? Although we have the monitor data and we have the electronic medical record, there is always the chance of minor but accumulating significant changes that may go undetected, perhaps because physicians are very busy in a patient who is even worse than the one presenting a deterioration. There's always reliance on human factor. Someone has to notice these changes. And then if we do not notice it when it happens, but we want to review it at a later time point, this is not easy because if things are not recorded and if we cannot see them all simultaneously, we cannot really easily understand what happened first and what happened next And that sometimes makes it is important to make decisions in care. The CDS user interface solutions offer visualization of biosignals from multiple sources, allowing the physicians to make these decisions and understand what's happening to the patients. It provides calculation of severity scores and other parameters of the disease course, for example, previous use of or even and failure of non-invasive ventilation, use or development of new renal failure, and so on. And predictive analytics that have been developed specifically within AEGLE identify patients at high risk of death, and specific alarms are present in this CDS. Now, the second issue that we have addressed is mechanical ventilation. Because mechanical ventilation is a supportive measure, we expect zero attributable mortality. Yet, mechanical ventilation has been shown, when inappropriately set, to increase morbidity and mortality. This should not be accepted, and this should not be the case. So we really need tools to help us optimize the delivery of ventilation. The problem becomes more intensive when patient is breathing spontaneously but assisted from the ventilator. In this case, the variability of the normal breathing pattern makes it even more difficult to detect when an injurious pattern is developing because of the constant changes. If you are in front of the ventilator screen and you see that everything is fine, that doesn't mean it will continue to be fine 5 minutes afterwards. So we need monitoring and analytics to help us with that. One of the two major problems have been identified and addressed. Sustained high driving pressures, high distending pressures have been shown to affect patient outcome. So far, there is no modality available to identify or alert physician for the presence of high driving pressures in assisted ventilation. And ineffective efforts, especially when they occur in clusters. Both of them are very important to determine patient outcome, have been associated with increased mortality, but in current care, we have no method or modality to monitor and identify this phenomena. So the CDS solution offers the computation and visualization of driving pressure along with other ventilator parameters. To further facilitate the physicians understand why a patient at some point might have developed high driving pressure, visualization of the ventilator parameters has been combined with other biosignals. For example, we could see if a patient is under stress when he has high driving pressure by checking the signal of his heart rate. Alerts have been developed for the risk of presence of high driving pressure based on analytics developed specifically within AEGLE. When it comes to ineffective efforts, we have developed a tool to visualize not only ineffective efforts, but identification of the clusters, the events that we have described in the literature, and of course the presence of alerts. We have also provided the physician with visualization of all PVI monitoring parameters because he needs to identify the cause of this cluster so he can perform more targeted intervention. Additionally, alerts based on predictive analytics for the risk of death based not only on PVI parameters, but also on clinical parameters have been developed and are present within this clinical decision support user interface. Now that is all for me, and I will stop sharing my screen now so that Achileas Chytas, who has done most of the work in the development, his team has been a major developer of this user interface, will present you, and we can take questions later. Thank you.
Hello from me. Thank you for coming. We're here at the first screen of the CDS UI. And before I start, let me tell you a little about some minor points of the architecture of the CDS UI. Firstly, it utilizes data and analytics that are located at the AEGLE cloud infrastructure in the way that when new types of data are uploaded at the AEGLE cloud infrastructure, the analytics are triggered and they produce the relative results. When the CDS UI realize that the results have been updated, the CDS downloads them and visualize the results. In a way, the system is lightweight, so the majority of the analysis is taking place at the AEGLE infrastructure, which is scalable. And at this CDS level, the only requirement is the visualization that happens. So in that way, the CDS UI is completely portable. It can be installed on a different server. Right now, it is run locally on my computer. And since it is browser-based, it can be even accessed by a tablet. Perhaps with some minor modification for the usability on a tablet. Regarding the actual CDS UI, the first aspect is the column on the left, which shows some information. The first thing we see is the option to select the number of beds that are available in the ICU units. Right now, the maximum for our iconic ICU unit is 7, so we can set the number of beds as we so desire, up to the maximum number. At a later version, the physician will have the opportunity to assign specific patients to specific beds, as it would be the actual case. Afterwards, the physician has the opportunity, the ability to select an individual bed, which, in a way, it is a patient. Below that, there are some basic demographic information like the gender, age, etc. And afterwards, there are some tabs that represent screens that most of them are one or two major analyses. Now let's move on to the top bar of the screen. We can see the 7 beds that we have assigned. And we can see that 6 of them are marked red and 1 is white. This is a level of alarm, meaning that at 6 of our 7 beds, there has been some kind of alarm. We don't know exactly what it is, but it exists. In order to see what type of alarm there is, we must select the corresponding bed. In this case, we are on bed number 1. Moving again on the left tab, as we can see the analysis, there is a triangle in front of the analytics, and again it is marked either as white or as red. Again, it represents that the presence of red triangle. It means that in this specific analysis there has been 1 or more alerts, while the white means that there is nothing wrong in that section. Moving to the actual view of the interface, we are currently on the nutrition single tab, which represents the nutritional analytics and information of a single patient. You can see that there are 2 alerts, 2 types of alerts right here. There is firstly this one, which is a pop-up alarm that has some minor additional information, like this triggered by the nutrition tab and it refers to calories. This type of alarm represents an actionable alert, meaning that there is something currently wrong with the patient, and the physician has can do something to alleviate this situation right now. In this case, perhaps the physician can increase the amount of calories that are being given to the patient. The other type of alert is this text right here. It is a simple text that it says patient duration detected, and it is actually the result of our predictive models. In this case, the model that uses demographic data, hospitalization data, and data features extracted from nutritional data. And it estimates patient mortality. In this case, this based on the nutritional data that the patient has had received for the first week of hospitalization, has shown that that patient is likely to die. If we scroll down, we can see the types of features that have been used for the creation of the model. Not all of them were selected for the model, but there were among those. It is the physician has scrolled down because this information can be useful, but it's not something critical. It is complementary. What we see in the screen, we see for our duration of the hospitalization, currently days number 10, but the data are anonymized, by the way. We can see the amount of information regarding proteins and calories, and we can change what type of information we see using this drop-down menu. Right now, we see the actual intake of of our two values, meaning that on the first day there were zero calories, 0 proteins. On the second day there will be 250 calories, etc. The difference means the deficit. It is usually meaning that the difference between the requirement of intake and the actual intake. As we can see, it is mostly negative. Moving on the second tab, this is not part of an analysis. This is mostly depicting many data together. And what it is right now that we see is the nutritional data for all the patients, for all the selected beds we have. The two charts represent the left one represents the current day, and the right one represents the whole days since the start of the hospitalization. The chart represents the percentage of the requirement that has been achieved for the current day. As we can see, we can select to see either proteins or calories. For example, today for a patient on bed number 5, we achieved the 54% of the protein requirement. And for the others, that value was 0. This information also exists at the table below, and with an additional information that represents the quantity that should be provided to the patient in order to achieve the desired threshold. For example, a patient on number 1, we should provide him 200 and something and 3 calories in order to achieve the desired threshold. And the desired threshold is set right here. It is currently on 20%, but it can change by the physician. And as we change it, the tables are updated and also the charts. And the charts read again on the chart, meaning that this value is below the threshold. Moving on the next analysis tab, it is the drug administration tab, which represents the analysis based on the biosignals and drug administration data. These two are combined together because some drugs have, of course, an effect on the physiological values of the patients. This is also an actionable alert, which is the product of a model that has been developed that examines features based on biosignals and some specific drug administration, and looks at the 8 last hour of the patient, the current 8 last hour, and detects if something is, if the patient is experiencing some kind of deterioration. And as we can see here, this model has detected that this patient is experiencing some deterioration, and actually this is data from a patient that has died within their last 8 hours, so it might be apparent from the values. And we can select different parameters and different drugs. It mostly gives, apart from the alert, it gives the doctor the ability to, like the previous presenter said, to examine signals from different sources, drug administration and biosignals. On this tab, this is again not the product of analysis. It's at best case the product of some calculation like the Apache score, soft score, if the number of ventilation days, and if or not it was successful. Some of them are static, like the Apache, it's calculated on the first day of mission. Some of them are more dynamically, like the total days of ventilation, which can, of course, increase. And these are also features that have been used with additional other information in order to create the models that we talk about. We can move on a different patient. The charts and demographics are updated as well. And here we can visit the PVI analysis, which is a mechanical ventilator. This aspect of the analysis is to identify patient periods of time where the patient had experienced trouble breathing, which is represented by the blue line, which is a signal called ineffective efforts, meaning that the patient for some period of time had problems synchronizing with the ventilation, so he didn't actually get the breaths he wanted. Again, there are two types of alerts here. It is the actionable alert right here. It indicates that there is an E event located, meaning a large period of time with where ineffective effort were clustered together, and it has been shown from previous analysis we have performed during the AEGLE that patients with that type of cluster have increased mortality. Here the physician can compare the the signal, the ineffective effort signal, with some other signals that are present for our analysis. They can be visualized, and they also provide some additional information. And we will talk about it on another patient, but right now I would like to talk about this slide bar. Right, the ineffective effort event is currently set on the last that has been detected, but the physician has the opportunity to also browse previous ineffective effort events in a case he or she wants to get some additional information regarding that patient. Moving on a different patient, again on the PVI aspect. Again, there are the alerts here that there is an effective effort event located, which is only one, it is this one. And now let's talk about this table, which provides some information regarding the compare of the ineffective effort signal and the signal we have currently selected. There are some metrics that means distance means how much it resembles from the time spectrum analysis. This represents how much the signal matches. There are some additional information regarding the mean values before the event and after the event, and whether or not they were within normal boundaries, because some of these values have boundaries that are within after some threshold can be deemed as harmful. What is might be also interesting on the physician is this information right here. It's called frequency delay index. It represents that if the signals are found to match each other, if the changes on one signal follow the changes on the other, and it gets the value from -1 to +1, and close to -1, meaning that the selected signal changes before the ineffective effort does. So in a way, it can be indication that changes on the KF signal are responsible for the changes on the ineffective effort signal. In a way, it is provoked by it. And as we can see at this zoom-in screen, perhaps we can see by just a rise that the green line is changing prior to the blue line. At least for the beginning of the event. Afterwards, things might change, but at least for the beginning, we can say that it is more or less clear that this is the case. So this is what the actionable alert here does. It presents the information that there are such events like ineffective effort cluster, and provides some information on what might be causing them, so the physician has some additional insight in order to perform the actions needed. Again, scrolling down, there are a set of other data. There are actually features that have been used for our predictive model regarding the PPI analysis. Using, again, features regarding from the PPI and features from the electronic health record and hospitalization records, we have developed a model that in a way predicts patient mortality based on those information. And for this patient, it has detected that the patient has a high risk of death. Moving on a different patient. As we can see here, we are on patient number 5, which is white, meaning that he has no alerts. And as you can see on the analysis, are also white, no alerts here. He doesn't have a PVI analysis, but he does have a benefit analysis. And since they are both ventilators, they are mutual exclusion. This is also a case of combining data from two different sources. In this case, I'm combining data from a monitor and data from the ventilator. And the physician can again select the signal he desires and visualize and check about and browse them in order to get some additional information. Besides that, there are some results of the analysis we have performed, meaning in this case that we detect periods of constant values that are deemed as harmful. For example, this detects periods of high driving pressure event. It provides some basic information when it was detected and what was the values, etc. If we move on to a previous patient, we can see there is also an actionable alert here, meaning that we have detected that the patient is experiencing an event of low compliance, constant low compliance for quite a long period of time, 2 hours, almost 3. And this is indication that the patient has experienced some trouble and can be harmful. So the alert indicates that exactly that perhaps the doctor should look into that patient and make some changes, either regarding the ventilation settings or some other action. This is all from me. Thank you.
Thank you, Achileas. No questions for today. Thank you very much, everyone, for participating in this webinar. We are reminding once again that you are very welcome in the conference we're organizing in Rotterdam in May, where you can see the final version of this platform being demonstrated, as well as demonstrations of many other solutions presented for the healthcare domain. Thank you very much for participating. We will send you the video of this webinar together with some questions to evaluate what you have seen. Have a nice day. Bye-bye.